Okay. Any questions? Arlene, for you, looks like you took the probability and statistics before, right? Your probability course and all that. So it looks, I got the impression it's a little bit boring, the class. So, okay. When I start this Friday, hopefully, using the first order and second order method, I'm not going to give you any additional my lecture note. I prepared also and preparing, but that's sufficient. Then I don't think you need my lecture notes, because I'm going to really finish this up. Plus, then you will get involved in really a project. Then you can program, then really execute the program, then maybe MATLAB, MATCAD. Then 3 of you as a group will generate the nice project. Then that's what I want to see. So everybody familiar with the MATLAB or MATLAB? You familiar? Yes. Pretty much, right? How about Songtae? Yeah, I think well, you can learn, as you start the program, you can discuss and learn. It's not difficult to pick up. But Arlene, you use a MathCAD, no? You use who uses a MathCAD? Who is not coming? Jingyu. What happened to Jingyu? Still sleeping? Okay, I'm going to finish this, both the random situation today and one case for correlated case. So all 3 cases we started already on Monday, so I'm going to really finish this up. Okay, so for the normal and normal situation. So this is the case for we started already normal to normal case. And the reliability is just a continuation, is 1 minus probability such that safety margin is less than equal to 0. And this is, or you can write as 1 minus probability of failure. Margin is, of course, a random, the variable, which is sigma y minus sigma s. That's the situations. Then here you can write this from that portion, which is 1 minus infinity to 0 Fm x dx. It's a clear description. Then here, this is normal. Because this is a normal, then this is a normal, then this is a normal. That's the beauty for normal distribution, and this is kind of the last time to write the expression for normal and normal. So I'm going to write one more times. What's the BM? Standard deviation of safety margin. 2 pi and exponential function minus x minus mu m over the bm square dx. Typical, nothing, anything wrong here? I have to do equal 1 minus. One last time I'm going to show you the expression is change of variable. Let's say z is equal to x minus mu m over the bm. Then you take a differentiation dz over dx is equal to, just differentiate that portion, is 1 over bm. So inside here is a z. Then from here the dx is equal to bm dg. So what's the process doing this? What's the reason doing this change of variable? This is like a transformation from the regular expression for normal distribution to the standard normal distribution. So in the when you start the first order reliability method, this is the approach, that's what we are using it. It's called Rosenblatt transformation, which transforms from the general expression for the probability model of the random variable to the standard normal distribution. Then you have to use this change of the variable. So after this, you put that right in there. Then you can express R as 1 minus and minus infinity to minus mu m over the bm. Then you got the same thing, bm square root of, I have done this before here, so it's nothing new, but this is going to be last time. I'm going to do once again because this is so important. So bm cancels up. Then you can see the standard, the standard normal distribution minus mu m Bn, this is mu, this is or this is equal to 1 minus phi. You can move this guy to down there. Then you can express as minus 1 over mu. Yeah. Coefficient of variations on that one. So everything squared away with the expression reliability is equal to 1 minus PF, important, 1 minus 1 over. It's very much well simplified if the both random variables are normal distribution. Always go back by the change of variable, go back to the expression using the standard normal distribution because all the information is done. For the phi, this is everything back to the 0. So mean is equal to, this is like Fm, this is like M. Mu M is equal to 0. Standard deviation Bm is equal to 1. That's the situation, right? When you make a change of variable, then everything is all shifted to the 0 origin and the axis. Then after that you can solve the problems and things like that. And you can also compute, you can express the Bm. Bm is standard deviation of safety margin. Of course, this is B sigma S square plus B sigma Y square. Then I'm going to just use a couple more lines for this. Take out this guy, then you have to divide it by this guy and square plus S square B sigma S square B sigma Y square. Then you can just do the massage through. Then you can get the result like sigma S mu sigma S square plus mu sigma Y square and 1 square. What's a mu here? Mu sigma S square. What's a mu here? Coefficient of variation of sigma S. And what about the N1 there? That's a central safety factor. So central safety factor N1 is equal to if I just write this notation, which is the same thing, y e to the sigma s, or which is really same as mu to the sigma y, sigma s. Okay. You can just take a variation. This is a really expression for standard deviation of m expressed in terms of such a variable. Then R is always like this, right? This is a phi minus. If you look at the Isaac Elishkov book, I think chapter 5, I think, their expressions, I don't know exactly where it's wrong, but this is correct. Okay, my note. If you find any mistake, let me know. But this is, as far as I know, this is correct. And you can cast the expression, you can use this expression into here. You can have that simple expression, the mu m as the expression, mu m is equal to mu sigma s mu y minus mu sigma s, right? Correct? Then you can have this expression if I just write down the final. I got this is, check back your which is same as up here. Lots of times expression using the coefficient of variation is very useful, and using the N1 safety factor, then you get the feel already when you get the actual numerical value for this, then you can really predict the outcome without really do all the calculation. If this is a large, then you got problem. Okay. If this is a large, what happened? If mu is a large, dispersion of the loading is terrible. If this is a large, then what happened? The quality of the material is a problem because its uncertainty is too much. So before even you compute, you have to think about changing the material type with a better quality materials. Because yield is dispersion, you are not going to expect a good design, and reliability level would be terrible. It's going down significantly. So by looking at that and using this is not the mu N1, okay, then the central safety factor, central, that means it's really ratio of the mean. Ratio of the mean. then always I want you to develop engineering judgment or ahead of computation. A lot of things you can really say something on that, especially on the structural reliability is concerned, because it's not doable. If the component level, as I mentioned, you can redo it, or you can just change the component. But for structure reliability, for structure failure, you can't just change because the system collapses. So that's what you have to be kind of careful. Yeah. I don't catch you. Say again. You wanna come out here? Come on. Good. Yeah. So instead of the name, we say it's gonna be a singularity. Well, in this case, okay, this is for the M's safety margin. When you say this is when this is equal to 0, then yeah, this mu m. If this is 0, what happens? This goes infinity, isn't it? So yeah, of course. Then when mu m model is equal to 0, it switched to this type is okay. Yeah. I don't know. That's my answer. Very good observation. Then what I'm going to do, this is not just suddenly pop up, right? This has a history. This has a history saying that mu sigma s, sigma y minus mu sigma s. To qualify this is equal to 0, then this guy has to be equal to that. The yield has to be equal to the actual stress. Then this is equal to 0, which means there is no safety margin. I'm just thinking myself, right? No safety margin, right? Okay, no safety margin, what that means? What's the reliability level? It's about 0. So it's not going to work. But mathematically is concerned, that's what we know to get to know the standard normal probability function. That means this has to be 0, isn't it? For Fm, right? Correct? And this has to be 1. So this is okay because this is in the numerator. But this is equal to 0 or approach to 0. So it's almost equal each other. The definition of the mu m is concerned when this is equal to approach to 0, then this is going to be infinity. The coefficient of variation for safety margin is concerned infinity. So in such a situation, as we look back, on the verge of collapse, nothing to compute. In this case, it's okay. This is for the mu m is equal to 0. This is a perfect definition, right? But this is undoable. You don't need any computation. 0. And that's all I can tell. T1. That's all I can tell. The strength is equal to the stress, which means exhausted. The system is about to collapse. Yeah. That's all I can say. So, any questions? Is it clear? Clear. Very special cases. Okay, next is pay attention. For the log normal situation, both are log normal. The situation is still the part of the special case. I intentionally want to do this case because it's easy. Because both you can transform into the standard normal probability function. That's the only reason. As we will learn Rosenblatt transformation, that's so transform into the standard normal probability function. Everything back down to normal. Then you can compute that easy. So this case, sigma y, sigma s, both are log normal situations. For the log normal situation, you can write the probability density function for log normal distribution. You can write easily. Very close to the expression for normal. Sigma s is greater than 0. Of course, you can write also for the yield stress, it's almost identical. B sigma y 2 pi exponential minus half natural log sigma y. So this sigma y is a specific value of random variable sigma y. So A sigma y, B sigma y, but here is important, the definitions here. This A sigma s, there's A sigma y, B sigma y, and here is a B sigma y, B sigma s, B sigma y. What's the A sigma s here? Mean of? Mean of sigma s? That's the trick here. Not the trick. This is a mean of natural log of mu sigma s. This is standard deviation of natural log of what should I write? What did I write? Of standard deviation of natural log of standard deviation. This is a mistake here. Oh, no, this is a standard deviation of this guy, I should say, sigma s. This is okay. Mean and standard deviation of natural log of variable. Sigma s, sigma natural log. That's not just the sigma s, natural log of sigma s. And the same thing over here. So what this would be? Standard deviation of the sigma, standard deviation of ln sigma y. This guy is mean of so otherwise the processing procedures is all same. And also we did not derive, but you could possibly do. So here is a couple things you have to pay attention. Mean of sigma s is expressed as exponential functions of A sigma s. This is a relation between the variable sigma s square. And I want you to really look at my note, page 9-5, and the variance of sigma s is equal to exponential function. You have to, this is really all conformed. A sigma s plus b sigma s squared times this comes like this. One entity, this is exponential function b sigma s squared minus 1. Very clear. Then you can use, you can also see the expression for y very close. You can get the replace s to y, and variance you can have sigma y in the same way. And now reliability expression comes like this. Reliability expression is probability that sigma s is always less than definition, or you can write R as a probability that sigma s move this guy under y is less than 1. So a little bit change of variable. So I'm going to say let z is equal to sigma s over sigma y. Then R can be simply right here, probability z is less than 1, or I can say that probability, you take a natural log, probability ln z is less than 0. Equivalency, there's no differences at all. We know that z is equal to natural log sigma s from here, take a log, then ln sigma y. So as you know, for the log normal distribution, over here, this follows log normal distribution, this follows the log normal distribution, right? So now, as you look at, this guy follows normal distribution, this follows normal distribution, then this guy follows the normal distribution. So back into the pot for normal distribution, then try to getting into the form using the standard, the normal distribution. Then everything's all solved in that standard forms. Then after that you can compute for the case of log normal. So, so mean mean of Z is equal to let's go one more step. Expected value of natural log of the Z is equal to, of course you have to take a mean, then that is equal to sigma S A sigma Y, as is shown here. So that's what you got. And also the variance of Z is B sigma S squared plus B sigma Y squared. It's clear. Yeah, thanks. This is ln Z. Looks complicated a little bit, but nothing if you look inside. It's very systematic. So now you can write the mean of Z. Then you can write the variance of Z. But if I just write 1, EXP is already be wrote. This for easier, for the variance is exponential you can use this expression, you can use that expression doing that, and variance is pretty lengthy. This is exponential function of this times exponential function of B sigma S squared plus B Y squared minus 1. Get that expression is in my notes in there. It's pretty lengthy. Then all the elements that you must construct the reliability or the probability of the failure is all constructed. Then reliability is concerned is probability as we have done it. Natural log Z less than 0. And this you can express as a phi. Why? Why? Because natural log Z follows normal, standard normal distribution. Then you can get into the expression using phi right away, which is equal to 0 minus natural log Z, standard deviation, natural log Z. To use standard normal, everything has to be in natural log of random variable. Otherwise, doesn't follow. So here, then you can have this guy. Final expression is a minus. I want you to really check. Something could be wrong, but just to make sure you check. B sigma s squared plus b sigma y squared. And you can, using the N1, you can express reliability, including the variable of the N1. So this is, of course, e to the e. We can compute that. So log normal, a little bit transformation is key to do. For the midterm, I want you to follow, understand the log normal, how to use, transform into the standard normal distribution forms. Otherwise, it's difficult to solve. This is it for the log normal. Both are log normal situation. Okay? Question? Everything is in my note. So don't say, oh, everything is in my note. Then if you come for exam, I hate to say exam, but you have to really understand the whole process, then it's okay. Last one is a correlated case, which is somewhat different. But usually, as I mentioned before, applied stress and yield stress has virtually no correlation. In other words, rho xy is equal to usually 0 or very, very low. But if you have a situation that loading and the strengths are correlated, how to handle that? Instead of a variance, what do you expect to come in the equation set? Variance, if the random variables are uncorrelated, it's just variance you are using it. M is equal to R minus S. If there is R and S has a correlation, then you have to bring correlation coefficient. We learn at the beginning. And also, instead of variance, you have to bring the covariance. Remember? Who cares? For example, now back to everything is as a standard forms. The variance. The variance, you have to start from the definition. What's this? Definition, x minus mu x squared, isn't it? Or if you write as integration term minus infinity to infinity what? X minus mu x squared fx. That's what the original definition is, the variance. And when you talk about the interaction between two random variables, right? Strength and the load, x and y, let's say, you can say variance, but you have to think about covariance. Now this is a bachelor state, this is a married state. XY, interaction of SY, right? So that's what you expect, right? So expression, just a thought process. Not this, it's a single state. So you expect other partners' personality, you have to observe interaction. Covariance, two parameters. So this, I can write this guy as xy. Both are the random, the variable, right? So then in terms of integration form, assume that x and y are continuous, the random variable, then x minus mu x, y minus, so using small xy means a specific value for the random variable, capital X and capital Y. So now you have to write this guy so this becomes double integration. Simple. So this guy is a joint, whether this is a 2 variable, 3 variable, that's all joint probability density function. In this case, it's a 2 variable joint probability density function. If it is, independent, what to expect? Independent, DNT. Then this is equal to fx, x, fy, divorced, bad. So independent, statistically independent situation for x and y, this joint probability density function can be simply the multiplication, this guy. I think I'll continue Friday. So Friday we have a class. Why? Because I have to do makeup class, right? So have a class. Then I'll simply finish up the correlation case of Friday, then I'll stop there. And we'll include the midterm up to that correlation, the correlated random variable case. You can look up a couple pages from my lecture note. 2 pages. Okay? That's all we're gonna do. Okay.